Hello, wonderful people. Euclid released 27 scientific papers today. That's a lot of science. I'm kind of terrified to think what their paper output will be like next year when they have 30 times more data. In this video, we go a bit deeper into three key areas of those scientific papers, and we learn the very cool and, quite frankly, groundbreaking stuff they've been able to do. It's nuts to think how much they've been able to do with such a tiny sky area surveyed. For example, they've doubled the total number of strong lensing events we've seen to date in 7 days worth of observing. The three key areas we're looking at today are active galactic nuclei, galaxy morphology, and strong lensing. These are presented by Teresa Matamoro, a PhD student at the University of Bristol, Mike Walmsley, a postdoctoral fellow at the University of Toronto, and Phil Holloway, a PhD student at the University of Oxford. Welcome, Teresa, Mike, and Phil. Teresa, do you want to start by telling us about what Euclid has been able to do in the field of active galactic nuclei?
Thank you for having me. I'm very excited to be able to give a little bit of an overview of some of the work that the AGN group has been doing in preparation for the Q1 data release. Collectively, we've produced 7 papers, all testing different methodologies for selecting AGN and highlighting Euclid's capabilities for AGN science, which is very exciting. So to give a little bit of background onto active galactic nuclei, these are some of the most powerful sources in the universe. They are situated at the center of galaxies, and they are powered by the accretion of matter onto a supermassive black hole. And it is during this accretion that lots of vast amounts of energy and radiation are released into the host galaxy in a process that we know as feedback. And through this feedback, the released energy can then couple to the gas of the host galaxy and alter its properties. Now, AGN are rare. They make up roughly less than 10% of the galaxy population, but it is through this feedback that we believe that AGN are critical for galaxy evolution. And some of the reasons that we have to believe this would be evidence such as the M-sigma relation that connects the mass of the supermassive black hole to the velocity dispersion of the galaxy bulge, or simulations where we see that if we do not take into account this AGN feedback, we end up producing overpopulation of massive galaxies in the galaxy evolution simulations that we just do not see or we do not observe in the universe. So AGN are important for galaxy evolution, and in order to produce a realistic model for this, we need to understand AGN evolution in itself, and for this we need a complete census of AGN that we currently do not have. And this is because we do not have a single selection that can select the overarching population of AGN. And moreover, since they're rare events, we also require large survey areas, great depths, and high spatial resolution in order to be able to not only detect them, but also study their connection to their host galaxy. And this is where Euclid can come in, because with Euclid we gain all three of these qualities, which means that Euclid will open up the parameter space of AGN like never before. And using Euclid and the synergies it may have with other surveys, it will enable us to investigate a new era of AGN exploration. So to continue a little bit with this background, in preparation for the launch, the AGN group was already investigating what Euclid's capabilities were going to be in this field, and in particular they calculated the expected AGN surface density that we should be able to recover in the Euclid Wide Survey and the Euclid Deep Survey. And the main result can be seen in this plot, where we're showing the AGN surface density per degree square over the survey area of different missions. In blue and pink, we show the expectations for the Wide Survey and the Deep Survey. And the main outcome or the main takeaway from this plot is that with Euclid, we expect to detect a larger number of AGN for both the Wide Survey and the Deep Survey compared to other surveys that cover similar survey areas.
It's the diamonds that are the one on the left is the Euclid Deep, which has a smaller survey area but slightly better depth, so a bigger surface density, and the right one is the wide one over the full full sky that Euclid is seeing, or just a fraction of what Euclid is seeing? Or
Yeah, so the blue is the deep survey, the purple is the wide survey, and then the three markers are separated by the empty diamonds would be the number of AGN, well, the AGN surface density that we expect to be able to detect with Euclid, and then the colored in markers showcase what we should be, the AGN that we should be able to select using Euclid only photometry, so this would be the bottom markers, and using Euclid plus ancillary photometry. So using a combination of Euclid with other with ancillary photometry, we expect to be able to recover slightly larger AGN surface density. So yeah, with those results in mind and the new data in hand, the AGN group has used over 15 selection methods across the electromagnetic spectrum to select AGN candidates. Each one of these selection methods have their own strengths and weaknesses, but collectively we have found over 250,000 AGN candidates in the Q1 fields, which is equivalent to more than 350,000 AGN per square degree. And this is in line with the wide survey expectations from the Selwood et al. Results that we just showed. And this plot is basically just a snippet of the work that I've been leading, where we show the AGN surface density per square degree for different selection methods. And I also showcase the expectations for what should be detectable and what we should be able to select in the wide survey. Each individual marker represents a different selection for the different Q1 works, and then the markers are separated into the two magnitude bins represent the selections that we applied in the work that I led, where we separate in two magnitude bins to highlight that at the deeper magnitudes we obtain larger AGN surface densities, but potentially at these deeper magnitudes we're obtaining more contaminants that we're currently still assessing.
But this is actual Euclid data now. Like these are actual detected AGNs, not a...
Yes, these are detected AGN candidates, or selected AGN candidates.
What is it about the AGN that Euclid is seeing? Like, and I'll just use an analogy here. When people talk about like weak lensing, you start by showing these beautiful strong lensing images, and then you say that weak lensing is just a small distortion. And then when you finally see what like the actual weak lensing image that has been seen, it's like 7 pixels that are slightly grayer. And of course, you're just doing statistics to see that those 7 pixels are ever so slightly more squashed than the average 7 pixels when you look at a million collections of 7 pixels. When you talk about active galactic nuclei now, I'm imagining this image of this beautiful like stream, this jet coming out of the center of a galaxy. But I imagine that for most of these, it's actually, again, like just a statistical thing. Or do you have an example of an image of one of these AGNs? Or
I've got an image later on, but it really depends on the selection method that you use. So the ones that I investigated in the work that I led were mainly photometric selections. So that means that we're not looking at the images, we're looking at the fluxes and the magnitudes and the color that these sources have. So then when you get the colors from these sources, you can make a color cut whereby we know the area that QSOs, for example, which are a type of AGN, where these sources should be in a color space. So then we can make cuts to select them specifically. But that we also have methodologies that use the Euclid images to look at the center of galaxies, for example, and how much flux you're getting from it. So it's very exciting because we're already in line, if not surpassing, the expectations that we had for Euclid. And I think that before going into some details of the methodologies that we applied, the main takeaways that we should get from the work that we've done is that within the Q1 area, we're already surpassing initial expectations for identifying AGN candidates, that Euclid's capabilities will help us create a more comprehensive AGN census, and that the quality and the quantity of the data will allow us to explore a variety of methodologies for AGN identification, where we'll be able to study the candidates in relation to their host galaxies. Now I'm going to be talking a little bit about what we did in the work that I led, where the main goal was to create a multi-wavelength catalog of AGN candidates. This is sort of like the breakdown of the steps to do this. So we started with the Q1 catalogs that are just the MER catalogs, which I believe you've already heard about. And then from there, we do some cleaning of the data where we only keep those sources that have good photometry. So only the sources that had good flags. And then we perform counterpart associations with other surveys. And we do this using a nearest neighbor approach. And we match to this list of surveys that I have here. So Gaia, Galix, DES, WISE, DESI, SESS, and Spitzer. And once we have this multi-wavelength catalog, we then move on to the population identification, where we focus on whether a source is a stellar candidate or an AGN. The reason why we focus on stars as well is because when using color selections, stars can be a big contaminant. So by being able to select them and then remove them from the sample, we're already removing some of the contaminants. So to identify stars, we use a combination of the information that we get from the Gaia counterparts, in particular the proper motion and the parallax, and we combine this with the labels that we get from the Euclid catalogs, where we basically get the probability of a source being a star, a QSO, or a galaxy. And this gives us a good sample of stellar candidates that we can already flag and remove. And then with the leftover sources, we can apply our AGN selection techniques, where we apply a combination of color selections, spectroscopic diagnostics, or NSD fitting.
Maybe just explain what you mean by nearest neighbor approach for these other surveys.
Basically, you get your Euclid sources and you take a radius, so to get sort of like the area around your specific source, and you see what sources from the other survey fall within that area, and that's how then you can do the nearest neighbor approach matching.
Maybe it's just the word then that's misleading me, but the nearest neighbor is actually going to be that galaxy, just as seen by the other survey. It's not like a neighbor to that.
It will be the closest source that will be to your Euclid source from the other survey.
Which most of the time will be the same galaxy.
Potentially, sometimes depending on the resolution of the other survey as well, it could be that you have crowded fields, or that they make it a little bit complicated, or you can have resolutions that are, so for example, the WISE resolution is not as good as that of Euclid, so where WISE may see one source that is very diffuse, actually Euclid is able to see more than one, because the WISE resolution would merge them. So you have to take this into account when you do the nearest neighbor approach.
And then other than, you explain kind of why Gaia is very useful to have the nearest neighbor, the kind of same source or multiple sources in the Gaia field, because it helps you remove stars. What is useful about all the other surveys? Like, why can't you just soldier on Euclid alone and ignore Galix, DES, WISE?
The other surveys are interesting because then we can apply SED fitting using the extra photometry that we get from them.
Okay, what is SED fitting?
That's a spectral energy distribution fitting. So you get all of your photometric bands, and you can fit different models to model your source, which in itself can be used to identify AGN as well, or to cross-match whether a candidate that you've flagged as an AGN, maybe actually when you look at the photometry, the SED fitting tells you that it's something else. So moving on to the selections that we applied in this work, we mainly looked at color selections. This is because color selections offer an inexpensive and quick way of selecting AGN. So you take the fluxes, convert them into magnitudes, and by taking the difference between magnitudes, you get your colors, and then you can investigate these color spaces to identify those regions where your AGN populate. So in preparation for the launch, the Bisigello et al. Proposed a series of selections for looking at for selecting different types of AGN using Euclid-only photometry or Euclid and ancillary photometry, and we chose those selections that obtain the highest purity and completeness for both of these cases in the white survey, which would be these two top images that I'm showing. One problem that we had with this selection was that we were obtaining large amounts of candidates, which made us believe that removing the stars was not enough to take into account the contaminants. So we refined these selections by adding a morphological cut. So seeing as these selections were specific for detecting QSO type AGN, which are meant to be point-like, we combined the color cuts with a high probability of point likeness to make sure that there were no extended sources that were infiltrating this selection. And then we also made the most of the DESI counterparts that we had, because DESI, being a spectroscopic survey, provides us with reliable labels of whether a source is a QSO, a galaxy, or a star. So using those labels, we decided to come up with new refined selections using Euclid photometry alone and Euclid and ancillary. So we started by imposing a point-like cut. So we only wanted sources that were compact in order to refine the selection specifically for QSOs. And then we investigated the color spaces to find a cut that could separate the stellar locus from those sources that were labeled as QSOs according to DESI, and from the compact galaxies that were labeled by DESI as well. And these are the two cuts that we came up with, that actually we got a really good purity and completeness for both of them as well.
Every dot on all four of these plots is a dot that has passed the cut. Is that right? And then the blue versus grey is just after having made a cut, it's what you think might be a QSO candidate and what isn't, or is it only the blue stuff that is passing the cut?
So everything in grey has passed the morphology cut, so they're Euclid point-like sources. And then those that are in blue are showcasing what we consider to be QSO candidates, so our AGN candidates. And that's in the top. In the bottom, the all is similar, that all grey is point-like. The purple contour plot is showing where the stellar locus sort of lies. And then the blue points are those sources that have a DESI counterpart that has been labeled as a QSO. And the red points indicate those sources that have a DESI counterpart that have been labeled as a galaxy. And that's then how we can fine-tune these cuts to obtain a higher purity and completeness as possible. In terms of spectroscopy, we made the most of the DESI spectra that we obtained from the counterparts in order to try and select other types of AGN. We performed various tests. The first one was the detection of broad emission lines. In particular, we were looking for a broad hydrogen alpha, beta, magnesium 2, and carbon 4. And this is because broad emission lines are kind of like a telltale sign for AGN activity, because they're linked to the broadline region, which is a region close to the AGN, where you've got highly ionized clouds that are orbiting at very large velocities and therefore broadening these emission lines. And then we applied other types of nebular emission line diagnostics, such as BPT diagrams, or the one diagram, the blue diagram, or the gas diagram, that basically help us disentangle between different mechanisms of ionization. And these three plots here are just an example of the different BPT diagrams that we applied, and the different colors are showing the different population of sources that we select with the BPTs. I think overall with the DESI spectra we were able to select roughly over 5,000 AGN candidates. And then for SED fitting, this is where all of the extra photometry that we obtain from the nearest neighbor matching comes in, because we can then we can perform this SED fitting and obtain parameters of our AGN. In particular, there's one specific one that is the AGN fraction that is defined as the ratio of AGN flux to total flux in the mid-infrared, and this can be quite useful to then come up with a threshold of AGN fraction above which we believe a source can be a potential AGN candidate. So the way in which we investigated this threshold was by plotting the cumulative distribution over the AGN fraction for the different populations that we identified with the different methods. And in particular, we were looking at where the non-AGN candidate cumulative distribution was meeting the cumulative distribution of what we consider to be our most reliable AGN sample, which would be those that had a broad emission line detected in them. And then we fine-tuned this threshold to be roughly 0.25. And here I'm just showing an example of what the SED fitting would look like for one of our AGN candidates, and a nice little image of what this source would look like.
So this answers my question from earlier. And the AGN, if I'm not mistaken, is like the white thing right in the middle, and then...
Exactly. So this is where SED fitting and all of that extra photometry is really helpful, because from SED fitting we can then get a lot of different parameters from the AGN. And then sadly we don't have a lot of time, but there's other AGN works that are really, really interesting. I think they can mainly be separated into photometry-based ones and morphology-based ones. We've got works for identifying optical and near-infrared counterparts for point-like X-ray selected sources, a first study of red quasar selection, and even extending the quest for little red dots. And for the morphology-based ones, there's very interesting methodologies for identifying AGN using diffusion-based inpainting, investigating the first Euclid statistical study of the AGN contribution fraction, or a Euclid statistical study of galaxy mergers and their connection to AGN. Sadly, we don't have time now to go over them, but I recommend you to go and read them. And then finally, for what's next in terms of the AGN science for Euclid, we're now in the process of measuring reliable redshifts for these candidates, estimating their physical properties through SED fitting, and overall trying to obtain the statistics of these samples and take advantage of Euclid's spatial resolution to link the candidates to their host galaxies, as well as exploiting the synergies between Euclid and other surveys to select different types of AGN.
We're on a channel called Cosmology Talk, so tempted to ask, are there any kind of cosmological uses of this once we know more about AGNs? I mean, I know that baryonic feedback is a massive issue in all sorts of cosmological clustering probes. Will we learn more about AGN from this that we can then better constrain feedback models?
More things that we can learn from AGN, from their morphology. We can try and get an idea of the environment of these sources, and in particular the large-scale structures. So we can try and understand better whether AGN, we can predominantly find them maybe in filaments or in voids, or whether they're in the outskirts of clusters. So that's the sort of potential further on work that we can do as well to understand them in the sense of large-scale structures, for example.
I could maybe chip in as well on just Teresa's really cool catalog as a cosmology application. I think a lot of cosmological hydrodynamical simulations, universe and a computer kind of thing, they rely on AGN feedback. That is to say, somewhere in the code, they tinker with the numbers such that they add energy flowing out of these AGN into galaxies. And that's really important to make sure we get the right distribution of masses of galaxies from the simulations versus reality. And that's kind of a handcrafted number. So understanding what AGN we really have in the actual universe and how much energy they're kicking out is quite core to making sure those cosmology simulations are not fudging the numbers and really do line up. It would be very easy to tinker with AGN feedback and other things like generally called subgrid physics to make sure your simulations line up. And Teresa's catalog is and Euclid in general might be a useful resource for understanding how AGN behave, and therefore what might or might not be missing from our cosmological inputs in those simulations.
Let's move on to galaxy morphology with Mike. What has Euclid brought to the table with that?
Thanks, Sean. So the really fun thing about working on galaxy morphology is it's so visual. You can look at the pictures and see what we've measured. And actually, that's part of what powers our science, because we recruit members of the public to help annotate these galaxies. And you, Sean, I didn't tell you this before, you're going to help us annotate some galaxies right now.
And because I edit the videos, we'll only see the correct answers.
So this is the Galaxy Zoo website. It's a citizen science project. It's run for the last 15 years or so, and we've had more than 200,000 volunteers have joined in annotating galaxies. We've had more than 100 million responses from them. And this is what they saw for Galaxy Zoo Euclid. So here we have an image of a galaxy taken by the Euclid telescope. And the project asks a series of questions that are designed to guide people through describing the morphology, the visual appearance of a galaxy. So this is actually kind of a tricky one, but I'll help you out a little bit, Sean. So you can see the picture. You can also see a sort of sharper black and white version from just the Viz filter, just the bluest wavelengths that Euclid measures. And we also have this sort of low surface brightness enhanced one that kind of shows up the fainter features. So Sean, here's your first question. Is the galaxy smooth and rounded with no sign of a disk, or does it have some features?
I want to add a caveat that I'm totally aware of Galaxy Zoo, but have never actually done it. So this is actually my very first thing. I mean, it does look like there's an artifact. There looks like there's some sort of cosmic ray or something on the right there that is gone through. But you're not asking me that question at the moment.
I'm not asking you that one yet. You're right, because usually what we say is if it gets in the way of making your classification, we'll call it, a problem. But here, it's kind of incidental.
It looks like there might be a bulge in the middle, but I would guess smooth.
There's no spiral arms. There's not edge on. Clumpy is interesting. I might have said this has some clumps. You see these kind of star-forming splotches. This is trouble when you're a cosmologist. You don't look at little clumps of stars. But it is pretty smooth. Overall, that would also be a fair answer. How rounded is it?
The total image, I would say, is completely round. The sort of bright spot in the middle, maybe in between.
Yeah, but you're right. The galaxy itself does look pretty round. I agree, Sean. All right, last question. Is the galaxy merging or disturbed or nothing going on?
I mean, the pen and Timmy wants to say minor disturbance because it's not absolutely perfect, but I would say none.
Yeah, one of these two. I agree. So it depends if you consider this kind of asymmetries as some disturbance or just kind of part of how the galaxy works.
Do I get a grade at the end of this, or
Yeah, I'll tell you if you passed. So kind of to skip ahead, I guess, to the talk, we're taking your answers, Sean. So let's say here you picked maybe irregular, there's something funny going on, maybe something else. Hit done, get our next galaxy. So we showed them, as you can see in this example, without any what we call metadata, no coordinates. So we just showed the pictures, but didn't say where they were or what they were or their, the light coming from them, the flux, any serious astronomy measurements, just the image of the galaxy. And so we were allowed to do that. So you did pretty well, Sean, actually. I would say that you were bang on. And the nice thing about morphology is we disagreed at the start, right? I would have said, actually, there are some features there. You thought it was pretty smooth. But the nice thing is, what we can do is we can average our answers out. So here, again, we have the same set of Euclid galaxies. I picked about 100,000 here. And we can filter them by answers. So, for example, we might pick ones which have spiral arms. Might be a bit extreme. Here we go. So these are galaxies with spiral arms. And we can even say, like, how many arms do we think they have? Let's go with 2.
And where you've got this vote fraction, you're saying that at somewhere between 72% and 100% of respondents said it had a spiral arm.
Exactly. We asked, 4 people, 3 of them agreed with you, 1 of them agreed with me, and we got a 75% vote fraction. So this becomes a kind of proxy for confidence. Like if I crank this higher, they should look more spirally. Crank this one up as well. There we go. So see now these are pretty obviously 2-arm spirals. So that means that's why we ask many different people for the same galaxy. And this is a public URL, which your viewers are welcome to, you put in the show notes or something, people are welcome to play around with after once this goes live on Wednesday. See what you find. Now, I gave you a little sleight of hand there, because actually these are not the answers from volunteers. This is entirely predicted by the AI models that we've trained on what you and I and many other people said. So when I do, for example, picking galaxies that have strong bars, this is the predictions of our models to find galaxies which have strong bars, not what actual individual humans said, because there are just too many galaxies to show. For Q1, we could have just about done it. For the whole Euclid-wide survey, we're going to have something like 90 million galaxies that look like these, which is just impossible to look through. It takes centuries to look through that many galaxies. So we're taking the volunteer answers, we're using them to train models, and then the models make predictions on the rest of the Euclid survey. And so that means our volunteers are more useful than ever. It means that every answer a volunteer on Galaxy Zoo gives gets multiplied out 1,000-fold. The models can accurately predict anything the volunteers tell us. So here is some more examples of galaxies with strong bars. On the next slide, we have galaxies that are merging. On the next, we have galaxies that have some major disturbance. You can see these bright, they're called tidal tails, these huge arcing features often from galaxies that have merged in the recent past.
And all of this has been predicted by the AI model trained on people's Galaxy Zoo answers. Oh, wow, that's spectacular.
Astronomy, in many ways, is an image recognition problem. We see a 2D view of the sky, and we have to interpret what we see. And a lot of the last decades of work by astronomers has been on using sort of automated computer methods to try to interpret that. Things like Sursic indices, things like which are essentially assuming the galaxy has a function of the amount of light you get as a function of radius. So just assuming it's a disk with a certain brightness profile, for example. But in the real world, well, outside of astronomy, computer scientists have worked really hard on very sophisticated ways to interpret images. This is how, when you take pictures on your phone, Google Photos, it can say, oh, this is your mother-in-law, tag them. This is your cat, right? Galaxies are complicated, but they're not more complicated than the kind of objects you bump into in everyday life, in the vision sense. So we're using some of that technology here, and that's how we can replicate these human judgments accurately. And I'll just wrap up by showing a bit more detail about how we did that. Instead of training one AI model to solve each task, the trick to doing well at many questions is to train only one model to solve every task. So for every answer that a Galaxy Zoo volunteer has given, to every question we've asked, for every telescope we've ever asked it, we train one model to predict all of them. And by using such a large training set, all those examples, it becomes quite easy to adapt the models to new questions or to new telescopes. And the principle behind this is called foundation models. The idea being you train on as much data as you can at the largest scale as possible. It's called upstream. And then you apply those models to some particular, in this case, a particular scientific task. These are called the downstream models. And that's a much more efficient way to train models, and it works much better, which the next slide goes into. So this is really inspired by work on language models. This is a seminal paper, Kaplan 2021. And these figures are showing, essentially on the y-axis, is how good your model is at predicting the next word in a sentence, where lower is better. On the x-axis, you have on the left plot compute. So how much CPU, GPU cycles, how many operations your computer needs to do to train the model. In the middle plot, it is the data set size. So just how many proportional really to how many words the model's looked at. And on the right-hand side is the size of your model. So how many individual parameters describe your model. You might have heard of, large language models with billions upon billions of parameters. And the headline takeaway from all three figures is there's an extremely predictable, scientists would say a power law relationship, where if we increase any of these three variables, then as long as we have plenty of the other variables, we can predict how well we'll do. Performance improves smoothly with all three of them. And what doesn't really matter, and really surprised a lot of computer scientists, is it doesn't matter particularly the shape of the AI model. So models come in layers of neurons, and people spend a long time thinking about how to arrange those neurons to train the best models. But that turns out to be less important in many ways than these three crucial parameters. And if you want to maximize your compute, maximize your data size, and train the biggest model, it makes sense to train really one model to do everything and throw all your compute, all your data, and all your parameters at it.
Yeah, it seems very unsophisticated, just like bigger, more powerful wins. You don't need to have a clever algorithm.
Unsophisticated is not a bad way to describe it. It really overturned a lot of computer science thinking when this sort of was demonstrated, because people spent a long time trying to design clever methods to build better models. And this actually worked very well, and in a way is kind of an engineering challenge more than it is a research challenge. But this paper was done by an OpenAI team in 2021 around about GPT-3. And you can kind of hear the cogs turning in their head like, that means we just get more data and more, GPUs and train bigger models and they'll do better. And that's kind of exactly what they did. And that gave us GPT-4 and what's become the large language model revolution. And I think overtook academia in some ways by having a solid engineering team to put this together rather than sort of searching for the fanciest way to approach it.
I guess it doesn't rule out the possibility of someone finding a better algorithm that pushes you to a different power law 5 years from now or 6 months from now.
There's a literal bet between two famous computer scientists about whether the models behind this, called transformer models, will still be the best way to model language in some years from now. And we'll see who's right. Transformers are very simple, elegant, if you like, models. But various famous people, including Jan LeCun, who really pioneered a lot of deep learning work, think that there's something fundamentally missing from them. Why do you need 1 million examples of cats and dogs to learn to recognize cats and dogs when humans can do it in 10? That there's something we haven't understood about intelligence, and they might well be right. But I'll just kind of finish on the astronomy point that we're taking this kind of principle of making a general model and applying it in astronomy. We took a series of telescopes, all the volunteer answers to all the questions we asked for all those telescopes. We made the largest human-labeled data set by a long way ever created. And we spent 15,000 hours of GPU time training our models. And what we found is that just like in Kaplan's result, that regardless of your choice of model architecture, that's each of these slices going left to right, having more data gives us these power law improvements in performance. Then having more parameters is also helpful, provided you have enough data. So on the left plot, we're seeing performance where lower is better for 100,000-ish images. And on the x-axis, making our models bigger, and we don't really improve in performance. But on the right-hand side, for 500,000 images, making our models bigger, we do better. So as long as we're not bottlenecked by data, bigger models also help. And the models that we ultimately used for the galaxy morphology work that I presented, picking those galaxies, and as part of a set of models which Phil will talk about for finding strong lenses, actually they're the exact same models being used in different ways, are generalized from these base models and adapted to Euclid quickly. And that's how we can go from having Euclid Quick Release 1, looking at the first images around August, starting to look at strong lenses around, what was it, Phil, September or so, to having, we had the first actual Q1 release for strong lenses in November, if I remember, to having catalogs of galaxy appearance and catalogs of strong lensing in a matter of weeks and months after that, because we didn't need too many new labels to make our models work well on Euclid images. And really anybody could apply just the same technique for their science questions if they want to find, in fact, one of the AGN papers that Teresa mentioned does exactly the same thing, adapting one of these generalized models called Zubot models to find AGN in images from Euclid. So I'm hoping that this will give astronomers a new set of tools to understand images at Euclid scale for exactly the piece of science that they're trying to do, and shifting us away from here's the catalog towards here's the tools to make the catalog you need.
Cool. That's exciting, I guess, merging of human classification and AI. And hopefully that's how the future looks rather than AI taking over. Let's now move to strong lensing. And Phil, do you want to tell us what Euclid's done in that sphere?
So the science I'm most interested about with Euclid Q1 has been the search for strong gravitational lenses. So these are where the light from a background galaxy or quasar AGN is deflected by a massive galaxy in the foreground on its way towards the observer or the telescope. And this is called strong lensing when this deflection is significant enough to cause multiple images of the background galaxy. So you can see this on the nice example on the right-hand side, which is also in Euclid Q1 data, but was found serendipitously. This is a particularly low redshift lens, and you can see the four lensed images surrounding the central elliptical galaxy, forming an almost complete Einstein ring. So the purpose of the search in Q1 was to systematically search through the Q1 data to find more examples of systems like this. So strong lenses are really rare because they require the close angular alignment of two galaxies, the lensing galaxy and the background source galaxy on the sky. And you also require the foreground lensing galaxy to be sufficiently massive that it causes a detectable deflection. The more massive the lensing galaxy, the greater the Einstein ring, and the more likely that we'll be able to detect it with our telescopes.
When you say this one was serendipitously discovered, do you mean that we didn't already know it was there from another telescope, or was it even more serendipitous that like someone accidentally did something and then it showed up?
This is a NGC system, so it's a relatively well-known system, but we haven't identified that it's a strong lens. We haven't seen the lens arcs within it before, and it's only with kind of space-based resolution that Euclid provides that we can now resolve the Einstein ring at very close to the center of this galaxy.
But we had no idea it was there. And actually, they only found it in images from Euclid's performance verification phase. So Euclid had a problem with having ice deposited on the mirror, and they were trying to sublimate that ice, heat up the mirror, and get rid of it. And so they took a lot of pictures while they were doing that to see if they'd fixed the problem. And one of those pictures was NGC 6505. And somebody was like, oh, wait a minute.
Wow. Thank you, ice.
Yeah, this was very much not a search targeting lenses in these galaxies.
Phil did find it again later.
Yes. I should also mention that when we did this systematic search, this one was one that passed all of our cuts, which was reassuring.
Yeah, I was going to say that's quite a nice like a test of the pipeline.
Yeah, exactly. These are exactly the kind of systems that we want to find. So it was good to find those. But once we've found these lens systems, they're then very useful for a whole range of different science cases from cosmology. So if the background source is time varying, like an AGN or a supernova, then the difference in arrival times between the multiple images can tell us about the expansion rate of the universe, and from that we can determine the Hubble constant. If they're not time varying, then we can still measure, for example, the equation of state of dark energy, or do mass modeling of the lensing galaxy. So the shape of the lensed images and the manner in which it is deflected is dependent on the entire enclosed mass within the lensed arc. Both the matter that we can see, so the matter in stars, and also the matter that we can't see, which is dark matter or faint stars. And so we can model the strong lens systems and determine the mass distributions of both the stars and dark matter within these lensing galaxies as well. The kind of headline result was that we found 497 strong gravitational lenses within the Q1 data. So this is double the number of lens candidates we found with space-based imaging. So this was a really exciting result, and you can see that they've got a whole range of different morphologies and lensing configurations in these examples here. And this is one of the things that makes it particularly difficult to find these systems, because they can all look very different between the different systems that can occur. And so there's a number of different papers that have come out of this search. There are the 5 strong lensing discovery engine papers, which will be what I'll be talking about primarily. So this is the search methodology and main results from the galaxy lens search within Q1. But there are also 2 other really interesting papers coming out with this Q1 data release. One on focusing on automated modeling using neural networks, and the second on galaxy clusters as well. So there's a whole range of different science that you can do with strong lensing, and a whole range of different tools that we use to do that. I should also highlight that this, as you can probably tell by the number of papers, this was very much a team effort from a whole range of different groups within the strong lensing team of Euclid, from making the simulations, which have to be really complicated and complex to ensure that they accurately train the algorithms and machine learning methods that we employ. And going from that to training the machine learning models themselves, and then we also conducted a citizen science search that I'll come on to as well, and then finally there was an expert grading and a lens modelling stage as well. So this was we termed it the strong lensing discovery engine, because there were multiple different parts to this, and that gives us confidence that these are high quality strong lens candidates.
And when you say 497 lenses found in Euclid, and then you say that's twice as many as before, does that mean that half of these were already known, or is it 497 new ones?
All but a handful are new.
Yeah, so the Euclid will really kind of change the game when it comes to strong lensing. So it has two main benefits to it. Firstly, it's space-based, which means it's diffraction limited and has very kind of high resolution. You know, it's got a narrow PSF. So this means that we can find lens systems with smaller Einstein radii, which otherwise wouldn't be resolved. So, for example, in ground-based telescopes, these are often seeing limited, so limited by the atmosphere, and have much larger PSFs, and this causes blending between the lensing galaxy and the source galaxy. The lensed galaxy makes it a lot harder to determine whether or not a system is truly lensed, or whether it's a false positive non-lens. And another benefit of the high resolution is that you can do much more accurate lens modeling of it as well. So instead of fitting kind of relatively simplistic lens models to the lens candidates, and we can use more informative lens models that fit the data better and tell us more about the lens system. And the second benefit of Euclid is its wide area. So it will survey about a third of the sky, and so this Euclid really has the kind of resolution equivalent to kind of HST, but the scale that we often see with more ground-based telescopes like LSST when it comes online. So as you can see in this plot on at the top, so here we've plotted the number density of lenses on the y-axis and the area of the survey on the x-axis. You can see that the kind of small area, high number density, is HST, and also Cosmos Web very excitingly came out last week as well, which would also be in the same area. And then Euclid Q1, which is 60 or so square degrees, and we've already found 500 or so lens candidates. But this is only a very small fraction of the total area that Euclid will bring. And so with DR1 next year, we'll be moving from 100 or so lenses to tens of thousands, or 10,000 or so lenses. And then with DR3, we'll be moving to the 100,000 lens regime. And this will be really the kind of revolution of strong lenses. So then we can have large statistical samples of strong lenses taken by the same telescope. Whereas at the moment we have a few thousand strong lens systems which are taken by a whole range of different telescopes, and therefore have a whole range of different PSFs, etc. Then we'll have 100,000 all taken by the same telescope, which will be really exciting. So because strong lenses are so rare, we needed to carefully refine the search mechanism that we use to find them. And moving towards DR1 and DR3, this will have to be refined even further, because the data volumes will simply be so vast that we won't be able to individually go through all of the systems by ourselves. I mean, we can't already. So for the Euclid Q1 search, we sifted, or we started off with an initial selection of the brightest galaxies within the Euclid Q1 catalogue. In particular, we selected I think it was magnitude less than kind of 22.5, in the Fizz band, and this gave us roughly a million or so galaxies. We then applied a whole range of different machine learning algorithms to these sources in order to select the kind of most likely lensing candidates. And so these algorithms had a whole range of different architectures, so from CNNs, which are often used in lens searches, to a vision transformer, to a Bayesian neural network foundation model, which Mike has very nicely introduced already. So this was Zubot. So this was trained. This was a machine learning algorithm pre-trained, like Mike said, on galaxy morphology classifications, which were then fine-tuned on strong lens training data for the purpose of finding strong lenses. And actually, we found that Zubot was the best performing machine learning algorithm that we used in this search. That was kind of really exciting to see, and it really did perform pretty exceptionally well. So after the machine learning search, we then did a large-scale citizen science inspection through the dedicated Strong Lens project Space Warps. So this is hosted on the Zooniverse platform, like Galaxy Zoo. And for this, we were kind of delighted to have more than 1,000 citizens taking part to classify strong lenses, and we got over 800,000 classifications of these images, which was it was honestly really exciting to kind of see all that data coming in, and the citizens kind of really engaging in Euclid data and strong lensing science as well. After the citizen science inspection, we then and the machine learning application, we then did a further stage of expert inspection. So here, strong lens researchers went through all of the high-grade candidates from both the machine learning algorithms and the citizen science, in order to grade which ones are the likely lens candidates and which ones are, like I said, particularly interesting within their own right. And then finally, we did a lens modeling stage. So here, we took all of the likely candidates and did automated lens modeling of them. So this not only gave us lens parameters of our lens candidates, but also acted as a nice verification step for the previous stages. For example, by suggesting images which did or didn't have counter images in the lens model, we could use that to determine whether some of the candidates that had a high grade were likely to be lens candidates based on the modelling. So moving forwards, the search strategy will have to continue to evolve. So in this Q1 search, we very much took a tiered approach from the automated lens modeling lens classification by machine learning algorithms, to citizen science, to expert grading, and then lens modeling, going from search methods which are quick to apply to vast amounts of data to ones which are much more time consuming. So moving towards DR1 and DR3, the citizen science and expert inspection stages, which have a finite inspection budget, will then move towards only the highest grade candidates from the machine learning algorithms. So Q1 is 0.04% or 0.4% rather of DR3. In this search, the citizens inspected 100,000 lens candidates, so about 10% of the images that we showed to the machine learning algorithms. But come DR1 and DR3, the data volume will be much larger, but the inspection budget will probably remain of a similar magnitude, hopefully bigger, but it will probably be of a similar magnitude, and therefore we'll very much only be inspecting the highest likelihood candidates from the machine learning algorithms. And this is kind of demonstrated on the plot on the bottom. So here we've got the number of lenses that we found as a function of the rank from Zubot, the best performing machine learning algorithm. And we move from a stage on the left where expert experts have inspected all of them to a stage where citizens have inspected all of them to a stage where only the machine learning algorithms have seen them. And one thing I should highlight is which systems we show to the citizens and to the experts can materially affect how many lenses we find at the end. So in this search, the citizens were the best classifier out of them and the machine learning algorithms. So they were the best classifier we had, but their inspection budget is limited. And so which ones we choose to show to the experts and the citizens materially affects how many we'll find.
I guess if you wait long enough, the citizens can do more, like by 2050.
Yeah, I mean, the one thing to note in this search was that it was done over a very short amount of time. So the citizen science search was set up and conducted over a period of only a few months. So come DR1 and future data releases, we'll certainly be running these projects for a lot longer, so then we can find more lenses. And for example, Galaxy Zero has been running for many years, multiple different projects, but it has been running continuously for many years. So yes, certainly having more time will certainly mean that we can boost the inspection budgets. So as part of the lens search, we also investigated which lenses we found and which ones we might have missed. As shown on the left-hand side, we show the distribution of the Einstein radii of the lens candidates, so these are in the filled histograms, compared to the simulated detectable population within Euclid, so these are the unfilled histograms. So as you can see, the histograms closely match up at the high Einstein radius end, so this indicates that we found the vast majority of the systems that should be detectable within Euclid Q1. But at the low Einstein radius end towards the left, there is a much greater difference. So this indicates that we might have missed systems for which the lensed images are much closer to the center of the lensing galaxy. So what this indicates is that if, for example, we had used lens subtracted images in our lens search, we might have actually found many more lenses. So by lens subtracted, I mean if we fitted a model to the light profile of the central lensing galaxy and then subtracted that light model out and then just inspected the residuals or showed the neural networks or citizens the residuals, we'd actually might have been able to see lens darks much closer to the center of the lensing galaxy. And so, yeah, that's certainly something that we'll be investigating in the future for future searches. And on the right, we also investigated which types of strong lenses will have passed each of our cuts. So here on the right-hand side, I've plotted the lens selection probability from the citizen scientists as a function of both the signal to noise on the x-axis and the Einstein radius on the y-axis. So on the right-hand side, at the high signal to noise end, where the citizens are correctly identifying the vast majority of the test images as strong lens systems. So I should note that the points on this plot are simulated lens systems, so we know that they are strong lenses. Whereas at the time, the citizens didn't, at the point that they made the classification. Whereas at the low signal to noise end, it's a bit of a different story. So if the Einstein radius is large, the citizens will most likely find it. But if it's a small Einstein radius and a low signal to noise, so particularly faint lens dark, for example, then it's more likely that the citizens would have missed those citizens. And we see a very similar plot with the expert grading stage as well. The plots show a very, very similar trend. So one of the super interesting things that we found within the strong lens catalogue was particularly rare configurations of strong lenses. So we found 4 double source plane lenses. So these are where a lensing galaxy has deflected the light from 2 background sources, galaxies at different redshifts. So these, by their very nature, are even rarer than the typical galaxy-galaxy strong lenses, which require the close angular alignment of 2 galaxies. Here we're requiring the angular alignment to be close between 3 separate galaxies. And this forms kind of multiple rings around the central lens. So these are particularly interesting because they probe the matter distribution at multiple different radii of the lensing galaxy. So we can determine, for example, the density slope, so the mass density slope of the lensing galaxy. And it's also possible that we might be able to constrain cosmological parameters from these as well. And separately, we've also found many examples of edge-on lenses. So these are rarer examples of lenses because they have a smaller cross-section than the typical early type elliptical galaxies, which are very massive and therefore more likely to significantly deflect the background light. And these are also really useful from determining the axis ratios of dark matter to verifying or determining verifying different theories of dark matter and modified gravity, for example. So each of these systems has much scientific merit within and of themselves, and so it's super exciting to have found these particularly rare candidates within the lens catalogue that we have.
A kind of left field question. You've got double source plane lenses. Is there any possibility, or has it ever been discovered, like double lenses, where like one galaxy gets lensed by a galaxy and then again lensed by another galaxy on its way to us, or is that just...
Yeah, so that lensing configuration can happen, and actually there was a recent paper where dubbed the cosmic zigzag, where a background source was lensed by two galaxies and actually formed a zigzag in its deflection angle on its way to Earth. So yeah, a particularly rare configuration. But yeah.
You were mentioning measuring the Hubble constant with these strong lenses. I guess you do need to follow up with some telescope that measures them more often. Are there any telescopes that can do that with the angular resolution to actually resolve them? Or is it the case that once you know they're a strong lens, measuring the like time dependence with a telescope that can't resolve the lens is still okay, or does it still need to resolve the lens?
Yeah, so one of the things about time delay lenses is you do need accurate measurements of the time delay between the different lens sources. So ideally they would be resolved, and you could see, for example, if it's a lens quasar, you would see 4 different images, and you would measure the time delay between each of those different 4 images. So, for example, with the LSST survey, which is starting later this year, that's exactly what that will be able to do. So it's going to be taking multiple images of the sky every night, and going back to the same position, I think, once every 3 days or so. And so it will be able to form these time series in order to build up measurements of the time delays for time varying systems like lens quasars or lens supernova.
Does it have the angular resolution of Euclid though, or?
It doesn't. So LSST is ground based. So there's certainly investigations going on into whether, for example, machine learning algorithms can be used to deconvolve some of these images to achieve higher angular resolution than is typically achievable with a ground-based telescope.
Yeah, I was wondering even whether you need the angular resolution. Like if you know from Euclid that it is a strong lens with 4 images, then you can look at it with something like LSST, and like you know that it's the sum of the original galaxy plus 4 periodic ones. Could you then kind of like extract from that the difference in time just from the one image?
That sounds like it should be possible. I've never done it though, so...
In a statistical sense, but yeah, okay.
Yeah. I think it should be, although I'm not 100% sure that there's not some caveat there.
Yeah, and even if it's low statistical significance, once you get to the point of having like 100,000 of them...
Exactly. You can kind of start to cross-correlate between time series.
Yeah, so my last question was then, like with 100,000 strong lenses, are there some like general relativity tests that become possible that nothing else can test that particular aspect of general relativity?
With, for example, the edge-on spiral galaxies, that's certainly something that people are actively looking into, and I guess we'll have to see what they come up with, and fingers crossed.
I think it's also, it gets a bit cosmological for me too, but I think that one idea is this thing called the mass sheet invariance, something like this, Phil, where for any particular lens, you can't tell the difference between either a different expansion in the universe, cosmologically speaking, that would explain the redshift versus angular distance we measure from the arcs, and a different mass foreground lens, which would also change the angle of the arcs. And for a certain change in mass, you can always reproduce the expansion of the universe. And so there's this inherent degeneracy in any one lens. And that's why we need a lot of them. I think the hope is that with a large sample, we know what kind of masses they would have to have. And so we could statistically unpick that degeneracy over a large sample. And the nice thing about double source plane lenses is they help unpick that on an individual lens basis, because then you have two background galaxies which were lensed by definition by the same foreground massive galaxy. But that's another hoped solution for which we need many lenses, because those double ones are so rare.
But if you've already got 4 with Q1, then with DR3 you must be getting thousands.
Yeah, we're expecting roughly 1,000 to 1,700 double source plane lenses with DR3.
Yeah, and I think we know now of order a few, and we just got 4 more. So
thanks everyone for watching. If you can't get enough Euclid science, there was another cosmology talk by Euclid today, covering the overall science goals of the collaboration, as well as a summary of today's data release. So you should definitely check that one out if you haven't already. If you have already checked it out, you might like Desi's Year 3 BAO results, which also dropped today. Other than that, thanks Teresa, Mike and Phil for telling us about this great work that Euclid has been doing.
Thanks for having us, Sean, and hopefully see you next year for DR1.
No, thanks a lot for having us. This has been great.
Yeah, thanks for having us.